Okay, welcome back to Lecture 12. This is the 12th lecture in Introduction to Advanced Macro Analysis. Today, the objective is to take a closer look at the stochastic growth model, the so-called RBC model, as a important paradigm for thinking about the macroeconomic world and thinking about way agents interact with each other. It's a simplification, of course, like all models, but has turned out to be quite influential in our way of viewing the world. And some of the tools we'll learn in this, in the next couple of lectures will be applied to the new Keynesian DSGE model that we will ultimately tell you to think about hard as being the current working horse or the workhorse of macroeconomics today. What I'm going to do today is, after a brief review of last time, as usual, I'll talk about the background and history of the stochastic growth model, the RBC model, in order to make you understand why it's such an important innovation for macroeconomists and for thinking about the world. It's dynamic. It involves strictures involving fundamental assumptions about how agents interact with each other. They obey budget constraints, they're consistent in their behavior, and they form rational expectations. They're going to try to anticipate the best they can those prices that affect their well-being in anticipation of their happening. And if they do so, this of course limits the amount of freedom the government has to influence agents' decisions. I'll start with a general setup, and I'll talk about the utility maximization for representative household dynamically using the capital stock as a vehicle for savings, as we've talked about throughout the course, except in infinite horizon. And at the same time, the household employs the capital in the sense that it owns firms that hire capital and labor. Some of the labor comes from the household itself, and the capital comes from the household itself. So it's a bit of a highlight of the weaknesses of the representative agent setup, but at least it points clearly to the incentives of households owning firms to maximize profits, and therefore the firm will be assumed to maximize profits. The firm has constant returns to scale that sort of restricts the amount of profit the firms will earn in equilibrium in relation to the other factor price, which is the wage, and therefore we'll end up focusing very much on a competitive setup in this model, and in the end, the most important factor that drives the model's dynamics going forward is the way the production function converts labor inputs and capital inputs into output. And this production function is moving all the time. It's shifting, and these shifts give rise to incentives, for agents to defer consumption and invest, produce more, work harder, produce more for the future, and when there's more in the future, there's more to be saved, possibly, or consumed. Households want a smooth consumption, and therefore the capital stock grows and the economy accumulates the effect of the shock over time. I'll try to characterize that outcome in the sense of a decentralized market equilibrium, because this economy has perfect is assumed to be in a setting of constant returns to scale, and non-convexities are absent in production, we would expect, and the absence of externalities, that the market outcome is a Pareto optimal outcome, and therefore it's possible to think of this decentralized market equilibrium as being identical to the planner's outcome. The planner would choose, it's generally like a statement of the first welfare theorem, the market outcome is Pareto optimal. Not necessarily it's the best you can think of for anyone, but it's the best for any agent given what the other agents are doing and not wanting to hurt the other agents. Because all agents are identical in this model, this is a very simple way of eliminating all discussion of distribution effects and focusing on the macroeconomic aggregates as averages. If I make it to this point, we'll talk about Loglinearization, which is how to approximate this this model, which is not linear at all, to make it amenable to analysis using the computer or using some numerical programming to figure out what the dynamic behavior of this model would be in equilibrium under the assumption that the agents understand the model and work with it. And to do that, we need to learn how to log-linearize continuous functions. And this is a basic technique that's used all over in macroeconomics, and there's no exception here. Last time we looked at stochastic difference equations in a very generic sense, and we took the ASAD model as kind of a way of motivating that. And the idea is that Slutsky and Frisch and other people have thought, 100 years ago, thought about the business cycle as being the accumulation of shocks, random shocks that no one could have anticipated at the time, but gave rise to dynamics that would propel the economy forward in a regular wave fashion. That was the Slutsky insight. We started with a deterministic difference equation to show that even a system that has no randomness at all, if it's away from its steady state, its particular solution, the model will have some dynamic adjustment towards that solution. Or if it's an explosive model, it will move away from that solution in finite time. And in infinite time, it would move infinitely far away from that steady state. We're going to focus on models with a steady state and with dynamics that give at least some probability of getting to that steady state. In fact, starting with deterministic difference equations is a great way to get that idea into your head. A single permanent disturbance, which could be thought of as the seed or the constant that gives rise to the particular solution of the difference equation, and then the rest of the homogeneous solution of that difference equation is the dynamics around that steady state or that particular solution. We extended this to a first order vector valued equation. So if you can think of the variables that interest us in economics are output as a deviation from the steady state or inflation, and maybe even another variable you might care about, you can put them in a vector form and make that vector depend on its own past and some disturbance. So this very flexible way will be a way at the end of the course, we'll discuss how the new Keynesian models can be rewritten. And to solve those, often we have to resort to a computer or some sort of, maybe the method of undetermined coefficients to solve that model. We spoke about the matrix that multiplies the lagged value of that vector as being essential to understanding the stability properties of the model. You should really take a look at that. It's relevant for the exam. The behavior of the model is determined by the eigenvalues of that A matrix that pre-multiplies the vector's lagged value, subject, of course, to the additive shocks. But when those eigenvalues are all inside the unit circle, the model will always converge to the steady state, if you like, the particular solution of the model, or the model in the univariate form, the particular solution in the steady state that we discussed. That's a fairly general rule. All all characteristic roots of the system, or all the eigenvalues of the matrix A lying inside the unit circle, is a global stability property. And if you remember, we showed that some models don't have real valued solutions. They may real valued roots. They may actually have pairs of complex conjugate roots, and the stability condition simply requires that those complex conjugate numbers that characterize those roots, that are those roots, lie inside the unit circle. So in the Cartesian plane of a real part and an imaginary part, the distance to the origin has to be less than 1 for stability. And then I tried to translate the ASAD model that many of you learned in macroeconomics into these terms, and we showed that there's very intuitive dynamics that arise from this somewhat simple model, but it's simple in the sense that it could be relevant for any future time in your life, including the final examination. And that most importantly, that one of the things that nails down the behavior of this model is the behavior of expectations, whether those expectations are volatile, whether they're kind of a backward-looking, moving average of the past. We'll come back and talk about that now. Expectations are important because they embody the anticipations of the future policies of the government and the central bank, because those agents, the central bank and the government, actually affect agents' well-being. And as we've already indicated in the other course, in the other part of the course, that if the agents misperceive the price level, then they may actually do very well. They may also do very poorly because they just didn't understand the real compensation for their labor or the real return on their productive assets. And in that sense, they really will care and try to invest some time and energy, especially if inflation is high, when the price level of goods in terms of money is rising. They want to make sure that they perceive future prices correctly and don't supply too much labor and maybe somehow lose large chunks of their assets because the prices have changed. This means that agents care. Okay, so agents care if they think the central bank is running a very high rate of inflation in order to stimulate agents to work harder without raising their nominal wage demands. This kind of means that agents that do not anticipate these shocks will tend to regret it. So conversely, one could imagine that anticipated policy can indeed have an effect, but only if agents are locked in with contracts or have taken decisions based on information that was old and no longer up to date. So in a sense, the dynamics and the way the expectations of future inflation adjust is part of the dynamic story of macroeconomics. Macroeconomics can emerge because the capital stock is sticky. It can emerge because it takes time for agents to decide, or maybe it takes time for labor supply to increase or decrease, but it's basically also a possible explanation that agents require time to adapt their expectations to a new reality. So if inflation in Germany rises to say 6 or 7% for many years, agents will start asking for higher wage increases. People who lend money to banks and put savings in a bank account will ask for interest rates that reflect higher rates of interest, and they will do whatever it takes to avoid being hit by the inflation, which means they'll probably end up buying goods and services in greater amounts and drive up those prices as well. That's a lesson of the OLG model that we discussed a couple of lectures ago when it's applied to the monetary environment. So in a sense, we have a new mechanism for Slutsky. Slutsky told us that random shocks are propagated through the system, so we have to have a good economic model. The propagation mechanism will also include the expectations formation of agents, and therefore agents that correctly anticipate the implication of shocks and the pricing of future goods and services in nominal terms will cause the economy to behave differently than if these shocks were completely unanticipated and ignored for many periods. So it seems like having rational expectations might rule out certain types of business cycles, but it need not necessarily rule out all business cycles, because despite the anticipation of agents of various changes, the economy may still have reasons that shocks are propagated. And we saw one already. One was the capital stock. Okay, if agents are unduly optimistic or expect the rate of inflation to be too low and borrow lots of money from other agents, or start investing in real capital at a higher rate, that will lead to an expansion of the capital stock, which may not be sustainable when inflation is correctly perceived. So this is another reason we can think of expectations as being an important force, which is the subject of today's lecture as well as in future lectures. So I'm going to try to explain why the expectations paradigm is so important. I mean, we can think about the ASAD model. How did inflation get into that model in the first place? Well, we had this notion that the aggregate supply curve conditions agents' behavior. Given an expectation of inflation of 5%, or given longer-term contracts which embed 5% inflation, then an agent that sees its wage rising by more than 5% would perceive an increase in the real wage, or a profit that is rising faster than 6% would be 5% would be perceived as an increase in real profits. Therefore, understanding how this inflation expectations term is formed is absolutely crucial. So in the ASAD model for undergraduates, we just took a simple modeling trick, which makes it also very easy to solve algebraically, and you can even plug it into your Excel spreadsheet or your MATLAB program to get some results. It's just a way of getting you to understand how the inflation expectations term matters, or how what we call core inflation matters. Here we just assume that it's a simple moving average of two inflation rates, today's inflation rate and the past. You're kind of assuming that this theta parameter would capture lying on in the open interval between 0 and 1 would be very important. So if theta gets very close to 1, agents are extremely well apprised of the price levels in development and don't get fooled at all. This would imply basically not just rational expectations, but perfect foresight. Okay, that's one extreme. The other extreme would be the agents simply take their expectation of today's inflation, given that they can't observe it, would be yesterday's inflation, last period's inflation, okay? And that would be the case of theta going to 0. Okay, that's kind of what we put into the mill for ASAD for you to look at and chew on, but you can also think of an alternative form, which is, again, subtle and different, definitely different. One could assume that the inflation that agents expect or act upon, given that they can't observe it directly, is a mixture of the last period's expected inflation plus some reweighting involved with the actual observed rate of inflation. So this is what was called adaptive expectations when I was first studying economics. And you can see that it's different from the previous one because basically theta now parameterizes how sluggish inflationary expectations adapt to the changing environment. So a theta very, very close to 1 would imply a very long time before agents actually move to some new level. So it would have to be a really persistent deviation of pi t minus 1 from pi t minus 1 tilde to get agents to move their expectations in the direction of inflation that's changing. On the other hand, the notion of theta being close to 0 would mean that agents are certainly adapting in a very mechanical way, just as in the last time, as in the previous example, but also in a kind of mindless way. So they're not really incorporating any other knowledge they might have about what the government or the central bank or what the economy is up to, and therefore it's not exactly a very friendly view about the way economic agents process their environment. This difference matters, and I urge you to try it out for yourself. You can try to solve this model with pi tilde, with core inflation depending on its own lagged value. So you end up having a third state variable, third variable in the vector that you want to analyze. You'd end up getting very different conclusions, especially since theta now has a different function. It's not the same theta as in the previous model where theta was parameterizing the correct perception of the current inflation rate based on like nowcasting. I mean, actually inflation is much better forecasted now than it was several decades ago. You just have to go to the Atlanta Fed website in the United States and ask for the nowcast of GDP. And there are similar types of nowcasting for variables. But again, no one really knows what's going to happen, but you can see it happening much more quickly. So it's plausible to generate somewhat arbitrary business cycle dynamics just using the ad hoc assumption of expectations and how they're formed. So I'm not going to do that. So the point is that this was criticized. Early researchers had assumed almost outrageously that the theta in the first version of this or in the second version of this was equal to 0. So that meant that basically agents were just backward looking. And that implies that you can get very far along the Phillips curve, and the Phillips curve starts shifting, and you'll have a lot of potential for central banks to reduce interest rates, to stimulate the economy, and the economy returns very slowly. So this presumption that agents were irrational in forming their expectations, because it is irrational. If you knew what was going on, you knew the European Central Bank was trying to do this, you'd take action against it by demanding higher wages and higher other nominal prices in euros, and this would negate the intended effect. It would end up making the economy much closer to behave much closer or stay much closer to the vertical LAS curve that we had before. Okay, so in the 1970s, when inflation was rising and became quite high across the world, especially in the US and the UK, less so in Germany, but also less so in Switzerland, but still higher than it was before. This view that theta was close to 0 was criticized. In fact, the whole thing was criticized because agents were just presumed not to be very intelligent or not as clever as the economists who formulated the model. So that's not a great starting point to work with. So if agents understand the model, then they should be given the means to anticipate inflation as it evolves according to the model. So this is called rational expectations. And this is actually different from what I had in the ASAD model. That was kind of a hat tip to perfect foresight, which is also a bit too extreme as theta goes to 1. But on the other hand, rational expectations would simply mean that agents make mistakes, but they don't make them consistently. They don't make them in a way that betrays their rationality or belies their rationality or their ability to think about the model that we're teaching in this class. Okay, so the father of this idea was Robert Lucas, laureate, Nobel laureate in 1995. And you can read the citation from the Swedish Academy for having developed and applied the hypothesis of rational expectations and thereby having transformed macroeconomic analysis and deepened our understanding of economic policy. So Lucas's basic message was that agents should use all the information at their disposal, which does not mean all the information. We obviously didn't know that Russia was going to invade Ukraine on the 23rd of February 2022, but the day after we did find that out. So information is evolving over time, but agents should basically condition their behavior in a way that makes the best of their lot, given that they don't know everything. And there are 3 forms that I like to talk about. The strongest form is the agents actually have the model at hand that we're teaching today or in some other course. A weaker version would say that agents form expectations that are conditional on information that's available and maybe don't know the model. Okay, but they can gather the information they can, and they can run some regressions and make some forecasts, and that expectation will do better than just being stupid and not looking in the newspaper at all or not trying to analyze the data. And the weakest form is that agents just don't make systematic mistakes. So if they made a mistake today and they made a mistake yesterday, they'll use those mistakes to try to correct their expectations so they won't get burned again. Okay, so these are all 3 different ways of thinking about rational expectations. There are others that are more subtle, other differentiations of the hypothesis, but overall we're going to spend most of our time talking about the strong form because it's easy for us in a modeling world to think about. Okay, so we should probably think a little bit about the math that you've learned in statistics, especially as graduate students, you should know a few things that you wouldn't have known as an undergraduate, and that's why I can teach this a bit more aggressively. We think about a random variable as a mapping between some variable x and some state of the world. And the value that x takes in the state of the world s, and s is to be understood as a very large number of possible states of the environment. We say state of the world. These are things you cannot influence yourself. They're just given to you on a plate, and these little s, these states of the world come from a very large set of states of the world, capital S, and you can extend s in the time dimension. You can think of it in the spatial dimension. You can think of it as the cross of time and space, and a very, very large, infinite number of things that can happen under those two dimensions. That would be the set of the states of the world. So, one element of capital S might be it's raining today, it's cold outside, I feel lousy, and the economy is collapsing. That's one possible state of the world. You can apply a probability to that. That probability law we're going to call little f, and it can be, we'll be taking expectations based on that density defined on that set of states of the world. And that expectation, you can think of it as the integral take of the event over its possible domain multiplied by the density. We say taking expectations, so taking expected value. Turns out that expectations is a linear operator, just like the lag operator. It's linear in that the expectation of a sum of two random variables is equal to the sum of the expectations of those two random variables. And if you pre-multiply those random variables by two constants, the expectation of the weighted sum of those two random variables will be a weighted average with the same weights of those expected values. Okay? Similarly, the differentiation operator is also a linear operator, just a fun fact. So if you differentiate something that is being expected, that small change, because it's linear, you can take an expectation of that small change, and it is the expectation of the small change. Small change is of an expected value is equal to the expected value of the small change. That's just another way of putting it. We also want to distinguish between unconditional expectations. If you have the complete information set at your disposal and you still have randomness in the system, or if you have a subset of information that is helpful in forecasting or knowing the expected value of X, that's called the information set. And because we move forward through time, think of the information set as being the set of available information that we don't lose under the carpet, under the table. We continue to retain that information and use it to update our expectation over time. Okay, there's a lot of theory behind it that I'm not going to talk about, but it should be clear that E of X, the unconditional expectation is different from E of X conditional on I, and sometimes we'll use a subscript to indicate the information set available to the agents when conditional expectations are being formed. You'll see that later. Small, very important fun fact is that if we're moving through time and people don't forget that then information that is accumulated as we move through time is going to be useful for improving the precision, or it will certainly affect the randomness of the expectation that we're forming, because as you move through time, you get new information which will be helpful for forecasting a variable that you might have been interested in forecasting before but had less information. You didn't have that information. Okay, so suppose that J is an information set that is bigger than I, so that's the notation in the second to last line, then an expectation conditioned on this bigger information set. Okay. I think I got that backwards, actually. Let's try that again. Suppose that I is a larger information set than J. Okay, so that means that basically as we move through time, I'm acquiring information. So in t plus 1, I would be larger than information at t. We'll call that J. Then in that case, the expectation conditional on the larger information set is a random variable, and the expectation of that expectation based on the smaller information set J is just equal to the information set conditioned on the smaller information set J. Okay, that's called the law of iterated expectations. Okay, that's a useful tool that we'll use later on in the course. Go back to the AAD model and remind ourselves why this was a unsatisfactory. It's good for undergraduates because it focuses undergraduates' attention on the primary things that macroeconomics is about: output, the business cycle, deviations from trend, what causes inflation, how do we think about the current inflation. So these are things that could well be relevant for the exam, but there's something that they're things that you should have learned as undergraduates. The problem with both of these curves is that they're not based on optimizing behavior per se. The thrust of this course is to try to put some economic reasoning and some theoretical meat behind or on the bones of this ASAD setup. So aggregate demand, demand of goods and services forthcoming at some inflation rate is not based on microeconomic foundations, and nor is aggregate supply, which is also very hard to understand. It's going to be the basis of most of the rest of this course. It's really hard to explain even to your mother-in-law why an increasing rate of inflation would cause agents, all things given, to produce more output. That has to do with the way agents think about nominal price changes and the way they try to anticipate them in the future, not being able to perfectly adjust, as we've said already. Okay, so the key thing is that the aggregate supply curve is based on ad hoc information, expectations formation, the behavior of firms producing output and hiring workers, and the willingness of workers to supply labor is all sort of ad hoc and not really fleshed out. So the purpose of this course will be to try to get behind that. And if you think hard about it, think of the perfect foresight case. It's not the same thing as rational expectations, but suppose theta were very, very close to 1 in the version of the ASAD I discussed last time. That supply curve would be really a vertical line. Output would be basically at its trend value, and output, if there are shocks, there would be like white noise. There'd be random reasons for being on the left or on the right of the AS, long-run AS curve, but these would not look like a cycle at all. So we know that output doesn't look like that. That's what I've been trying to tell you for the past couple of weeks. It looks more like an AR2 process or even higher order around some trend. And there's no real good reason for that. If it's just expectations that are wrong, we need to do better than that. Okay, so the rest of this course will be about microeconomic foundations of the AS and AD curves. We'll start with, in a sense, with the AD curve, and I'll tell you why. But in all cases, we'll have rational expectations. We'll impose that. We'll impose some sort of micro foundations on the model. And we'll think about internal propagation as coming from different features of those models. Okay, so the stochastic growth model, the subject of today's lecture, will basically be trying to get into that model and thinking hard about the way it works. Okay, so you can think about this stochastic growth model as being literally a discrete time version of the same Ramsey-Cass-Koopmans model we discussed in continuous time about 3 or 4 weeks ago. Okay, and when I finish with that, we'll notice, hey, this model doesn't have any monetary sector. That is, for most people, a limitation. So maybe we want to think about interest rates, nominal interest rates, the money supply, inflation, and in that case, we have the motivation to go to new Keynesian models that are specifically adding a monetary sector where the central bank either sets the interest rate or, in some older fashioned models, actually supply the money in a stochastic way, injections of money into the economy. We don't do those kind of models anymore, but they're interesting as an intellectual history. So let me start with this picture. This is a picture of two Nobel laureates with the President of the United States in better times. This is in 2004, and this is Finn Kydland and Ed Prescott. Ed Prescott just passed away last year. It's a shame. He was a really underappreciated macroeconomist, gave rise to much of the macroeconomic focus on intertemporal optimization and models that are written down with an eye to thinking about how agents decide and try to anticipate what the government is trying to do. These two fellows got the Nobel Prize for challenging economics, macroeconomics, that had prevailed up until the 1970s by saying simply, do we really know that a monetary sector is necessary at all to generate cycles? So they took the most extreme version you can imagine by saying that imagine a world where there's money literally does not matter from the get-go. It's all about real prices. Agents don't use money. It's a barter economy. What kind of dynamics would a barter economy have if that barter economy was nevertheless involving trade-offs between leisure and labor, between consumption and savings and investment, production, etc.? Could we still get a business cycle? Of course, skeptic would say right away, no, you can't. It's impossible. We know that interest rates are mattering for the business cycle, and we saw the 1970s, the Fed put on the brakes, put the economy into a tailspin, but also stimulated the economy before that. Well, these guys basically said, well, we don't really know that economic theory rules out the possibility that business cycles might have nothing to do with financial conditions, monetary conditions. And again, it wasn't to say that all business cycles were due to these real phenomena, but it's the question, do we need a financial sector, a monetary sector, in order to get any sort of cyclical behavior? Because you saw already the ASD curve. If people have perfect foresight, it hugs the AS curve that's vertical, unless you have some story about why the AS curve is moving around. Okay, so it's a fascinating idea. And it's even more interesting that the guys said, we're going to focus on one fact about macroeconomics that people have not paid much attention to, even though it had been around for a couple of decades. Robert Solow in the 1950s, in a 57 paper, constructed data that he claimed under certain conditions to represent the productivity of the economy, holding factor inputs constant. So we call that total factor productivity. And we'll see in a second, this total factor productivity series that you can generate actually has cyclical properties. So there was a presumption that maybe, by these guys at least, that these fluctuations in total factor productivity might actually be responsible for the business cycle. Could be an input, just as Slutsky had the input of random influences in a model, an economic model, as a linear or near linear transformation of those shocks. Okay, well, Kydland and Prescott, a long time ago, this is an anniversary type of presentation. I mean, 40 years ago, they actually showed that this was possible. Okay, and the stochastic growth model is exactly that. It's just a way of trying to take the Ramsey-Cass-Koopmans idea, which we showed in the last year, can be decentralized as a competitive economy, as long as the agents don't have market power and are price takers. You can make a discrete version of this model react to new information And that new information causes the economy, just like in Slutsky, to move away from its long-run equilibrium, long-run steady state. And the fluctuations that arise can actually look like the business cycle. So that was the finding of Kydland and Prescott, and for that reason they were honored with the Nobel Prize. This is a model about supply shocks. Supply shocks driving the model. Demand is completely passive in this model. Demand is reacting to these shifts in the production function that give rise to an aggregate supply response. And demand, of course, exists in this economy, but demand is not being shocked. So we don't have demand shocks. We don't have shocks to the marginal rate of substitution of agents or to their preferences for leisure versus labor. These are additional features that could be added to the model. This is like shocking S in the ASD model and keeping D equals 0 for all time. Okay? Or if you're in a logarithmic world, it would be like the log of output. The multiplier is equal to 1, and the logarithm of that multiplier would be equal to 0. We'll find in this model, because of its special features, the model is no longer absolutely stable. So all eigenvalues of that log-linearized system that we'll look at the end of the hour and next week and in Leopold's section, these models are saddle stable in the same way that the Ramsey-Cass-Koopmans model was saddle stable in continuous time. Okay, so that's an interesting feature that will help us identify the adjustment path. It will be a unique adjustment path in the absence of future shocks. And of course, every period a new shock is coming. So the model will have this, it'll be buffeted by shocks over time, and that will result, a la Slutsky, in irregular waves that he talked about, just as he predicted. Okay? But the saddle path stability is an interesting feature because it implies that the eigenvalues of that A matrix that we talked about last time, and we'll talk about again, will have some eigenvalues outside the unit circle, but just enough to guarantee that the model doesn't explode. And we'll make more discussion of that next week. Okay, so the literature, the background, I mean, this is not a PhD course, but you should know that Kydland and Prescott are the granddaddies of this movement. Kydland is a Norwegian, Prescott was a US American. Prescott kind of doubled down in 1985 by writing a piece. He even claimed that 70% of the fluctuations in the US economy over the post-war period were due to shifts, random shifts in the production function, technology, and not due to monetary policy. That prediction or that discussion, that claim was hotly disputed and led to many attacks and counterattacks, and it's all not that interesting. What's interesting is that the possibility, the technological innovation, shocks, and again, this is a very broad idea. I'll talk about it in a second. It's not just in the narrow sense technology. It could be anything that affects the position of the production function given capital and labor. So it could be the relative price of energy. It could be the real exchange rate. It could be some sort of competitiveness due to deregulation or regulation. All these things are fair game for shifts to the production function. So the model is really very abstract. I think the work by King and Rebello, later on King and Rebello have a review in 1999 in the Handbook of Macroeconomics where they kind of summarize the state of the art, and things haven't changed that much since then. There have been many bells and whistles on this model, and the model has some important weaknesses, therefore it's not the end of the story. One of the most important weaknesses is it doesn't have the price level, because money doesn't matter, prices don't matter. The model has a built-in, hardwired neutrality and a super neutrality. So you can just forget the central bank. Money is just out there if you want, but agents have figured out completely how to deal with it. Changes in the supply of the means of payment do not cause the economy to deviate from its path. The most important thing you should remember is that the contribution of Kidlin and Prescott and their students was to think about how to solve dynamic optimization problems in a usable way, and this would carry on to the new Keynesian business cycle theory that you're taught in modern courses all around the world, and therefore the lasting contribution is really the method, okay? So what do we need to make this model sing? What do we need to make it work? We need things you need in microeconomics. You need some agents. We'll speak about a representative agent, so we'll assume away all heterogeneity. All agents are basically endowed with the same wealth. Okay, again, this is completely unrealistic, but it's just to get started, it's a great way to start, and to think about the incentives that affect agents' behavior in a very, very focused way. So agents, this representative household is a stand-in for all the agents in the economy. This representative agent has preferences. The preferences are what you want, and you want more of consumption, and you want more of leisure, and you want them for all time, and you're not infinitely patient, so you'd like to consume more and work less now rather than doing the same later. So these are the things that are going to guide agents' thinking about how to best plan their savings, investment, labor supply decisions. Okay, this is all basically going to be constrained by resources. You can't do everything you want because resources are not infinitely abundant. So if you want to eat more, you have to save less. If you want to eat more, you're going to have to work more, or maybe you'll work more tomorrow and borrow from somebody. But if we're all the same, that's going to be difficult. So again, technology, the transformation of capital and labor into output is really, really important. In every period, it gives rise to the ability to either consume or to put aside consumption, build up the capital stock for the future, and to enable future production. So shifts in that technology, as we call them technology shocks or technological shocks, either increase or decrease the available resources that capital and labor enable us to produce. And again, this model is extremely limited in its applicability. It's really more of a way of thinking about these forces, and then we move on. But in this particular example, we'll take a market structure that assumes perfect competition. So we will not have any monopolistic behavior either on the firm's part or on the part of workers. There will be no labor unions in this model or combines by firms. This is basically, just to get straight, the incentives also intensify the endeavor of making markets competitive and not having Amazon control everything. Then we have an equilibrium concept, which means we're going to have prices. So this model in the decentralized version actually does have factor prices. The price of the representative good is going to be 1 in period t, but in t plus 1, it's going to be something else. And the question is, how much of goods today do you have to give up to get goods tomorrow? It should be maybe less than 1, so if you save, you get some more. And that will be determined by an equilibrium where the rate of interest will be the mediator. The real rate of interest will be the mediator of the trade-off between consumption today and consumption tomorrow. Okay, so think about this representative agent and think hard about that. We need to think about the preferences of that agent. So next week we'll spend time talking about this in detail, but we're going to think about additive separable, time separable production and utility functions. So my utility today is dependent on what I consume today and what I enjoy as leisure today, okay? But that does not affect directly the marginal utility of consumption tomorrow or the marginal utility of leisure tomorrow. Okay, so that time separability is a convenient device. Kind of means that we can't get tired of consumption by consuming a lot. We only get tired of consumption in the current period, okay? But that doesn't mean that we can't change the model. This is an introduction to methods of advanced macroeconomics, and believe me, there are lots of intertemporal non-separabilities that we can introduce into this model. In fact, Kidlin and Prescott introduced one themselves in their 1982 paper which involved non-time separable utility over leisure. So the idea would be that if I had lots of leisure today and lots of leisure yesterday and the day before yesterday, I'm really getting tired of leisure. You know, I really want to get back, I want to maybe the marginal utility of leisure is really falling, and therefore I want to maybe do some work. That's a highly disputable way of thinking about it. We're not going to do that here, so we're going to use a simpler specification because this is one that is probably more relevant for future work, but still worth thinking about. So that time-separable production function means that we'll be taking sums of those utilities in each period, t plus 1, t plus 2, and we'll be discounting by some discount factor for utility. We'll call that beta. We'll come back to that in a second. Secondly, Cobb-Douglas production. So we're going to really Mickey Mouse production function, constant exponents. The elasticity of output with respect to capital is alpha, and the elasticity of the labor input with respect to that labor of output with respect to the labor input is 1 minus alpha. So this production function has constant returns to scale. It has Harrod neutral technical progress. If I increase Z, which is the productivity, the Harrod neutral productivity term in this production function, I increase the labor input effectively by 1%, okay? And therefore the output that I generate with given labor inputs would increase by 1 minus alpha percent. This type of technical progress characterizes well the technical progress we've had in the past 150 years. There's no guarantee that it'll work in the future, but it's one that actually guarantees that the factor shares to capital and labor are stable along the steady state. We talked about that in the growth part of this course. Okay? So in this model, think of L as the labor input, and labor input goes from 0 to 1. So 1 would be working all the time, 24/7. That's kind of unreasonable. L equals 0 means you're sitting on the beach all day. Somewhere in between there, think of L as the fraction of the unit period of time. We're going to be spending most of our time thinking about quarters. So a 3-month period, how much of that quarter are you spending working? L would be the work time. So doing that makes it convenient. Think of 1 minus L as the leisure input, and therefore what we have in the second term of this utility function is a power function with eta standing for something like the elasticity of substitution of labor supply. So it turns out that 1 over eta will be the measure of the readiness of agents to supply labor for a small change, temporary change in the wage that does not affect the marginal utility of resources to that agent. Okay, so that's just a hat tip or a tip-off for something you'll learn and study later. So here's what the model looks like formally. Expected utility in time period 0 is denoted by this E sub 0, so the expected value of what comes conditional on period t equals 0 information. Okay, and what is that utility? That utility is the infinite sum discounting by beta. Beta is the discrete form of discounting, so beta is 1 over 1 plus the subjective discount rate. Beta lies between 0 and 1, and that infinite sum involves a lot of terms, infinite number of terms involving consumption in that period, in period t, and work in that period of t. Work has a negative implication for utility. The more you work, the less leisure you have, the less well off you are, so you can see that it all works out. You could have put something in for 1 minus L and you get the same answer, but we want to try to make it very quick, get quickly to the punchline of this setup. Let me review the other equations quickly. Capital accumulation is a discrete time Goldsmith equation that describes the evolution of capital stock as a function of what I had already, less depreciation, plus my income, which will be the sum of labor and capital income to the household, minus consumption in that period, okay? And we'll show later that YT is going to be equal exactly to the capital income that the household has plus the labor income the household has. That's just the nature of the beast. Okay, and then the Cobb-Douglas production function I already showed you. And then the most interesting and important part of this model is the evolution of this Z, this Harrod neutral technical change. It turns out that Hicks, Harrod, and Solow neutral technical change are identical in the Cobb-Douglas case, but we're going to continue to call it Harrod neutral technical progress and Harrod neutral technological change, which means like suddenly I become more productive because maybe I'm using ChatGPT in my work. It makes me more productive. Or if my students are using a better form of word processing, they become more productive, as if there were more students. Okay? It's a special type of technical change, but it means basically that the marginal product of labor increases as if labor were in its quantity increasing without affecting the input of capital. We're going to assume that ZT actually depends on its own past, as is evident in this last equation. It's also dependent on some term that is constant. So the first term is a constant, and the second term is this dependence on its own past. So rho is an autoregressive parameter strictly less than 1 in absolute value and will generally be greater than 0. So it's kind of the persistence of the technology, the technological shock. Okay, and the third term is to capture this time trend in a way that in the steady state, the trend will be growing at rate g. Okay, so as t increases, this technology gets bigger and bigger, better and better, and when all the dust settles, we should be growing at rate gt. That's why the 1 minus rho is out there, because if you move zt, the log of zt minus 1 to the left-hand side, you can see that this 1 minus rho is the sort of the net new change in zt given zt minus 1. Okay, so when epsilon is the last part, that's the shock itself, the white noise random shock that propels zt, log of zt, in one direction or the other. So when epsilon t is absent, we would be on our way to the steady state determined by the path and where we started in the same way we discussed last week and 2 weeks ago in the case of difference equations. So this is a first order difference equation once you strip off the trend. We need to think about the market structure. I told you already the tradition in this field at the time was to ignore all market imperfections and market forms of imperfect competition, which may have had an undue influence on policy at the time. It turns out that imperfect competition is extremely important, as we're learning today, as we watch Amazon and Expedia take over the world. Increasing returns in production and in technology can be a problem. And still in all, we need to start somewhere. So we're going to start in a world that's really literally perfect. So there's no discussion about market power, because firms that would control this technology would have no market influence. The prices for output are determined by perfect competition. There's no imperfect information. And under those conditions, the same thing is holding true for the factor market. So capital is accumulated by households. It's rented to firms, and workers work for firms in competitive labor markets. So all these prices are going to represent their productivities in the equilibrium that we're going to discuss. In this sense, this economy will attain, and because it's a representative agent economy, will attain the Pareto optimum situation. Since all workers are identical, there's no Pareto optimality to discuss, because you can't, if all the workers are the same, if you make one better off, you're making all of them better off, and that's impossible because you've done the best you can. So it's a bit of it's a first cut at the discussion of where these dynamics come from. It's certainly not the last discussion. And as I said, in the most recent cyclical uptick of inflation, we've seen that market power seems to matter. There's a big literature that's growing that says that market power matters for the distribution of income. So some people do have more market power than others. Some agents own firms that have market power in charging prices to others. So this representative agent paradigm has its extreme limitations. But we have to start somewhere. We start with this. Okay? So we'll define prices and markets. Ramsey didn't have them. We showed that he could be decentralized. We'll call output GDP, right? We'll call it GDP. So after you take off depreciation, we'll have GNI, or we'll have net national income after depreciation is accounted for. You can use it for consumption and investment. There's no government in this economy. There are no taxes. All these things can be added and modified commensurately. Firms are owned by the households. So this representative household we'll discuss actually owns the mechanism by which capital and labor are converting those inputs into output, which is, again, consumed or saved by the agent. So it sounds like an incredibly intellectual contortion, but it's actually the most efficient way of dealing with this issue. You can assume two different families, but we have a representative agent. They would both behave the same way. One would be renting capital to the other, and the other would be renting capital to the other. The other would be renting, hiring labor from the other. But in the sense, it all sort of washes, and we don't have to worry about it. So you might say this is unrealistic, but it really highlights the incentives for agents to do the right thing. For the agents that are buying labor, buying labor if they're operating the firm, selling labor if they're supplying the labor, think of this W as the real wage, and the wage compensation in terms of the good that's being produced in period T. And similarly, the user cost of capital would be the gross cost that firms would have to pay to lease a unit of capital from the owner of that capital. So think of a taxi firm renting its taxi fleet to taxi drivers, and these taxi drivers would literally return the automobile after one period in a state that's not quite the same as it was when the car was or the automobile was rented, and that using up would be thought of as depreciation. So in a sense, the rate of return to capital in the net would strip off this depreciation, and in the market equilibrium, the willingness of households to accumulate capital and rent it to the firms that use the capital will be conditioned by this depreciation as well, just as it was in the original Ramsey model, or in the OLG model we discussed, the diamond model, at the beginning of the course. Now, if you think about it, the households are going to do this. They're going to maximize that object, which is a number. It's an expected value of a stream of consumption utility and a stream of leisure utility, which derives from their plans given the evolution of the state of the world over time. So it's a fairly involved problem, even in this very simplified form. The household has a budget constraint. The household has a budget constraint just like Ramsey had a resource constraint. Okay, and that budget constraint will basically condition the ability to produce output in the next period, because you need capital to produce. We know that from the production function, and you need labor to produce. Okay, so in any period of time, the agent on the right-hand side will have sources and uses. On the right-hand side, we have sources of resources, if you like, and we'll put it in the following way, make it easier for you to understand. It's the sources of resources for capital in the next period. So what can the agent do? The agent can have capital in the current period that it doesn't get burned up in the depreciation process like the taxi cab company renting the capital, the car, the Mercedes, and brings it back and it's got a scratch on it. Well, that's kind of depreciation, or it's not running properly. So you think of that as delta, the loss. So 1 minus delta is the volume of capital that can be used in the next period. Now, what else can the agent do? The household could take its labor resources, the resources generated through its labor activities in the labor market. That would be WT times LT. It's also renting out capital it already started with, so that would be UT, the gross user cost of capital, times T, at period T times KT. And now, it also maybe wants to eat something today, so it's got to subtract CT. And there might be some profits. They will be zero in equilibrium, but I put them there just to remind you that this household owns the firms. The firm is paying for capital, paying for labor. So what's left over after was what we would call, or what your microeconomics professors would call, excess profits or economic profits. Okay, but in a perfectly competitive world, under these conditions, I can tell you right now that pi t is going to be equal to 0. Okay, and for that reason, we'll eventually forget it, but it's in there just to remind you. And the this household starts in period t equals 0 with K0 capital. Okay, this household is renting this out not just today. Capital's renting out today at rental price U0 or UT in general, but also the whole sequence of prices in the future. So the price sequence will affect the household today, because if UT is high in the future, maybe it makes sense to save money, save resources now to have capital in the future. And if the wage is low today, maybe the household doesn't want to work so much. If it's temporarily low, maybe they'll work less. In future periods, they would work more when wages are higher. Okay, so there are two ways to solve this very complicated problem. Some of you may know from your previous courses or other courses, you can use the value function approach, some sort of form of we call the dynamic programming. It's another way of thinking about it. It's basically thinking about a two-period approach. I know I'm going to maximize utility today. I know I'm going to maximize utility tomorrow. Therefore, I'm maximizing utility today based on the notion that I'll be maximizing utility tomorrow with the capital that I've decided to carry forward. That's a sort of a PhD level way of thinking about this. I'm going to use the Lagrange approach, which you all know, and that's why there's a green arrow there. So I'll take this Lagrange approach, which will give us very similar results to our famous Pontryagin principle or maximum principle that we did already, except it'll be much easier, and you'll see that. We will use this latter, okay? We don't need to use the maximum principle because it's not a continuous time problem, even though the first order conditions will have similar intuition. Okay, so state the Lagrangian function. This is something you'll have to do on the final. I'll tell you right now. You got to set up the Lagrangian. So it's the same principles are involved. We have a sequence of budget constraints, not a single budget constraint, but every period t from t equals 0 to infinity, the agent has to obey this constraint that the capital stock tomorrow is equal to the undepreciated capital stock today, plus the labor income today, plus the capital income today, minus the consumption, plus eventually profits that might have arisen. As I said, we'll set those equal to 0 in a second. In fact, I will set them. Well, you'll see in a second. I have to define a sequence of Lagrange multipliers, each one having a subscript that corresponds to the period, and they have the same interpretation as in the earlier part of the course. It's the value to the agent in terms of utility of relaxing the constraint at the optimum. So given that the agent is doing the right thing, solves the problem properly, fulfills the first order necessary conditions, that's the value, the marginal value of a small relaxation. Imagine doing a helicopter drop of capital in period t equals 17, then lambda 17 in period t, in period 17, would correspond to the agent's increased utility at the margin deriving from a small marginal increase in capital in that period. Okay? Now remember, that's important because in any period t, the agent can't change the capital stock period in period t. It has to change future capital stocks by changing its current behavior. That's because capital stock is a state variable in period t. Okay, that's why the appropriate way of thinking about this is lambda t applied to kt, which is not under the control of the agent in period t, but in period 0, the agent can work towards getting the capital stock in period t to a different level than it might have been currently planned. So the first order necessary conditions require using calculus. So you're going to have to set the derivative of each one of those Lagrangian function with respect to each control variable in each period from t equals 0 to infinity. So it's many series of first order necessary conditions. Okay, it sounds awfully daunting. I mean, writing those down would require a long time and probably longer than you would have to enjoy this consumption that you're trying to plan. But in any case, we can still think about it. If the agent were doing the best she or he can, he would choose the path of consumption in every period t, the value of CT in every period of t, which gives you a path of consumption and a path of labor supply and a path of the capital stock in the next period. And that would fulfill the following first order necessary conditions. The first derivatives of all those, of the Lagrangian with respect to all those variables has to be equal to 0. So again, think about a big hill. When you get to the top of the hill in many, many dimensions, any marginal change in your control variable should not change the value of that Lagrangian, all things given, okay? So that means that the marginal utility of consumption is going to be equal to the Lagrange multiplier. Why is 1 over CT the marginal utility of consumption? Because we have a logarithmic utility function. Okay, so the first derivative of ln of CT is 1 over CT. On the left-hand side. On the right-hand side, we have the marginal utility of resources. So the agent should be indifferent between a bit of more consumption today and the value and utility of putting that in the capital stock, which would be available tomorrow. Okay? Similarly, the labor supply gives rise to an intratemporal decision, which says that the marginal utility of an extra unit of leisure should be equal to the value in terms of utility today of getting a bit more resources today. And that bit more resources is exactly what the real wage indicates. Okay? Because the real wage, if you work for an additional fraction of time, you lose the leisure. That's the marginal cost of additional work. But you also get the benefit, which is the wage times the utility you get over the resources that the wage commands. The last of these, the very last condition, of course, is just the Lagrange multiplier is holding in all periods because the agent doesn't waste any resources. Let's focus on the third condition. This is called the Euler equation, which means that the trajectory of marginal utility of consumption over time, of marginal utility of resources over time, which is the same thing as marginal utility of consumption over time, has to obey a certain trajectory which is connected to the productivity of resources in the future and connected to the marginal utility of resources in the future. So giving up a unit of resources today would cost you lambda t in utility today, but it would give you something tomorrow, which is beta, which is your impatience, measure of your impatience. The larger beta is, the more patient you are. Multiplying the marginal utility of the stuff you carry into the second period or the next period in use as capital in the future, you'd get 1 minus delta plus ut. Why? Because ut is the gross return you're getting paid by the person or the firm that's renting the capital from you. You have to depreciate it, so you're going to lose something. And then the resources you gain from that transaction will be giving you lambda t plus 1 utility in the next period. So the expectation of that product, both of which will be random variables, will give you the expected contribution to your well-being of forsaking 1 unit of consumption today. I'll make quick mention of this because I'm running out of time. I think we need to think about the usefulness of saving in the same sense that we thought about it in the Ramsey model. The Ramsey told himself, or her, the central planner, that she should not save for the sake of savings, because if you save too much, even if you're obeying the first order condition on the trajectory, you still might have too much capital in the very, very long run. Okay, and if that's the case, then it would be possible for you possibly to reduce capital in every period and make yourself better off, because if you reduce capital, you have more to eat, and therefore you can't have been maximizing utility. So this transversality condition wants to rule out all those trajectories of the capital stock that are inconsistent with the exclusion of that type of policy change. If I were hugging that path and I reduced K in every period by, say, 1%, that should not increase my utility. And if it did, that would mean that I'm not maximizing utility. So therefore, we want to make sure that the marginal valuation of capital in any period, as that period goes, as that time index goes to infinity, the marginal utility of a unit of capital has to be rising less rapidly than my impatience, which is given by beta raised to some exponent. Okay, so in some sense, my impatience will guarantee that I don't save for infinity. This transversality condition is the same onerous condition that we discussed in the continuous time model, but has the same interpretation. Okay, so if you're doing that and it's obeying the first order conditions already delineated, you're doing the best you can. Okay, and as I said before, profits will be zero, even though they're being returned to the household. They'll be zero because capital and labor earn their marginal product, just like in the original factor price frontier at the very beginning of this course. Let me finish up by talking about the Solow residual. The Solow residual is the motivation for Kydland and Prescott. They say that we know from Solow that the ultimate source of well-being in an economy is technical progress. And Solow himself argued that 50% of the U.S. technical increase in U.S. standards of living, GDP per capita, is attributable to technical progress and not to capital formation. So the U.S. got rich, certainly on the basis of saving and investing more, but that doesn't account for the entire increase in U.S. wealth measured as GDP per capita. And a constant returns production function tells you that, right? I mean, if you have increasing K and L, that gives you some Y, increase in Y, and what's left over after that must be because the production function itself shifted. And that residual is what Solow wrote down published in 1957, which made him famous, and Kydland and Prescott picked up and said, hey, this is kind of potentially, this deviation of growth in output attributable to factor changes from observed growth in real economic output should be some measure of the production function shifting back and forth. Under perfectly competitive conditions, it is. Okay, so it was a good idea. Here's an old picture of Germany that I used in one of my textbooks a long time ago. I love it because it's very beautiful. It shows basically that that output and the Solow residual track each other, even in West Germany, even in the 1960s, 70s, and 80s. Okay? It's still true today. So there's a suspicion that something's going on there that's in common, and Kydland and Prescott tried to push it very hard and say it's the shifting production function. There's a lot of resistance in the meantime. There are other explanations, but it's an interesting idea. And again, in the world of model building, it was innovative. Okay? So the firm basically is hiring labor, and the firm is hiring capital conditional on this production function, which is moving. So when Z is high, labor and capital are productive, especially labor. And that means, in fact, in the first instance, labor is more productive, and you hire more labor, then capital is more productive, so you're going to hire a little bit of everything. So that means that both U and W are driven by Z. Okay, so in the first instance, that will determine the firm's optimal behavior. And again, this is again to remind you that the profit of a firm producing competitively with this technology, the excess profit after the factors capital and labor have been compensated is zero. So this rationalizes why pi is equal to zero in equilibrium in the model. So how does that equilibrium look? After we've done this discussion and Euler's theorem and all factors, the factors capital and labor exhaust the national income after depreciation, or actually here with depreciation. So this is the statement for the gross national product. We can describe an equilibrium in this model. An equilibrium will be a sequence of C, L, KT plus 1, and the factor prices W and U at each period in T, as well as the Lagrange multipliers and this state of nature, ZT, such that all the first order conditions are satisfied. The transversality condition is satisfied for the representative agent. First order conditions for the firms are satisfied. The market clearing is satisfied. Goods produced are equal to the goods demanded equals goods supplied. And labor supply and capital supply are also equal to their respective demands. Markets are clearing, in other words, and the initial capital stock is given. That's an equilibrium. That's how we're going to define an equilibrium. And because of the factor price frontier, holding ZT constant, higher wage, lower rate of return on capital, and vice versa. Capital and labor exhaust GDP, profits are equal to zero, excess profits, so we can validate setting that equal to zero. Okay, so in a sense, we've given you the baseline, a very low baseline, because there's a lot to criticize. We'll do it next week for this model. This model is supposed to help us understand how a single factor that has nothing to do with government policy, has nothing to do with taxes, has nothing to do with monetary policy, has nothing to do with terms of trade, international exchange of goods and services. It only has to do with the production function shifting, is sufficient to generate a business cycle. Whether it is the business cycle or not is another question. But the innovation that this stochastic business cycle model represents was really quite important at the time, and it still is important today. We're still using the concepts and the devices and the framework to think about models in a new Keynesian world where there's a central bank, central banks matter, monetary policy is paid attention to, there's inflation because there's a price level. In the Kittle and Prescott world, there is no price level except the relative price, there's a price of goods, of labor and capital in terms of goods today, but a growing inflation, a growing price level determined by inflation is ruled out a priori because money is absent. Okay, so the subsequent lectures will refine that idea, and we'll be able to see why this is a very important midway point in this macroeconomic course, because we'll learn techniques that will help us understand the rest of the course. Okay, so we'll remember, we'll come back to stochastic difference equations, talk about rational expectations again. We'll use the RBC model next week to show its weaknesses, the way it doesn't replicate some of the features of the data, and then we'll talk about the things that survive. So we still think of the representative agent as a way of thinking about decisions made in a macroeconomic setting that are dynamic. Some agents may have complete freedom to do what they want, and some may not, so it may give rise to a reason to have two agents in a model. But right now we have a so-called rank model that we'll talk about next 2 weeks, the representative agent new Keynesian model. So representative agent introduced by the RBC world is still being used at the end of the course. We used the Lagrange, we used the optimization of the representative agent to give rise to a set of equilibrium conditions, and reminded ourselves that the factor price frontier under perfect competition actually implies that there are no excess profits in this model, so we can set those equal to zero. And this sets the stage for the discussion next week. Thanks for your attention. See you later.